Hello everyone, welcome to the 19th lecture on NPTEL course on scalable data science. I am Professor Saurangshu Bhattacharya from Computer Science and Engineering in IIT Kharagpur. Today we are going to see the third lecture on Spark. So, we have already seen, we have got an introduction on Scala and how concepts of Scala can be used in Spark, and we have also seen the motivation and RDD, and we have seen the concept of actions and transformations, and we have also seen some programming examples in Spark. Okay. So, we continue with our programming examples. So, we give two more programming examples in Spark, and then we go into the concepts of partitioning and accumulators in Spark, and then we go into details of implementation of Spark jobs and how actually jobs are run in Spark. Okay. So, the first example we are going to see today is that of collaborative filtering. So, the problem is the following, that you are given a matrix of users cross movies. So, you have a site where users are watching movies, and certain users have rated certain movies, and you want to predict the ratings of other users on these movies. So, basically in the matrix there are certain entries which are filled and certain entries are question mark, and the question is, can you fill in the question mark entries. So, a popular approach to solving this collaborative filtering problem is using what is called a matrix factorization model, which is to say that you factorize the ratings matrix R here as a product of two matrices. So, this is a user cross movie matrix. So, this is user cross movie matrix. So, the first matrix is a user cross K matrix, where K is the latent dimension, and the second matrix B is or B transpose is a K cross movie matrix. In other words, you have to find out some latent features for users and some latent features for movies, such that if you multiply this, so if you multiply for user U the latent feature, so if you take the user U features and take dot product with the features of the matrix B, mth column of this, you get the rating which is U B U R M B. So, this is the setting of the collaborative filtering. Okay. So, the algorithm for solving this problem is very simple. It is called the alternating least squares algorithm. So, we start with random matrices of A and B, which is the user matrix and the movie matrix. Okay. And then first we fix the matrix B, and then find A which optimizes the error on scores in R. Okay. And the second step is you fix A to the A that you have obtained in the previous step, and then you optimize for B such that it minimizes the error on scores of R again. Okay. So, you do this repeatedly, first fixing B and then next fixing A, and every time you update the B matrix and the A matrix, or the movie matrix and the user matrix. Okay. So, how you will implement this in Spark? Okay. So first, so the first simple implementation here I have provided is that you have the ratings matrix, which is a matrix in a local variable, okay, and then you create this A matrix, okay, which is matrix of random vectors, and also the B matrix, which is a matrix of random vectors. So, you initialize the A and the B matrix. Okay. Now, for parallel updating, what you do is you first parallelize the set of users. Okay. So, you want to update the vectors for each user. So, you pass the current B and the current R matrix, okay, and then in the ith machine. So, this operation inside the map is happening on the ith machine. So, in the ith machine you update for the user I, and then again you bring it back to the local machine, okay. And similarly you do this for each and every movie. So, you again the number of machines that you have, you parallelize the movies, m movies that you have into each of these machines. So, num slices here is saying how many machines you have. So, if you have 10 machines, you split the group of users into 10 machines, and then again for each user in that machine, in the ith machine, you update the movie vector using the optimization. So, both this update user and update movie functions are local functions which are running on each of these machines, and these are optimizing the vectors for this particular user or movie. Now, the problem with this implementation is that you are doing a lot of communication. Okay. So, every time you are sending the appropriate values for this ratings matrix, which is not changing. So, as you can see, the A matrix and the B matrix are changing, okay, but the ratings matrix remains fixed throughout this computation. Okay. So, how can we take advantage of this situation and not send these A and B matrix as a closure? So, because as we have discussed already, whenever you try to run a mapper function which is a closure, the whole variables, all the variables in this closure have to be passed to the corresponding machine where this map function is running. So, these are local variables on the controlling machine which have to be passed to the machine on which this map function is actually getting executed. Okay. So, so we want to avoid that. So, we implement this using what is called a broadcast variable. So, what is a broadcast variable? Broadcast variable is a variable which you can access just like a local variable, okay, but these are actually pre-distributed on all the nodes of the machine. So, whenever you say that this, you declare this rating matrix which you have read using, let us say, read rating matrix function as a spark.broadcast variable, Spark as and when required will send this the values of this matrix R on or rather it will send the whole matrix to all the servers on which the jobs are running, and instead of R now you just have to use R dot value, because dot value actually gives you the value of this broadcast variable. So, R now is actually a broadcast variable whose value field actually contains the matrix, and it is stored in each and every server, and rest of the code remains as it is. So, then you can see that this the ratings matrix does not have to be transmitted to each and every server all the time. Okay. So, we take the another example, which is the example of log mining. So, here the idea is that you have various users who are so you want to search interactively for various patterns in an error log. Okay. So, so the first task is basically that you read the lines of the error log file using the text file command, as we have seen already. The next is that you read or you filter out the lines which do not have error, or rather you filter the lines which have error, and then you store these errors RDD after getting the messages into this cached messages. Okay. So, we have seen this part of the code. Now, suppose you want to get a error message which has, let us say, the term foo. Okay. So, you want to get the error message which has the term foo. So, you call on this cached messages the filter command, and then you call the count command. So, because you call the count command, the action happens. So, then this RDD is materialized, and you want to count basically the number of error messages which contains foo. Okay. So, what will happen is that all these blocks will be created from the cached RDD. So, this entire code will now be executed. Okay. Up till now, up till this, no code has been executed. So, up till this line, no code has been executed. Now, it will, or rather code has been executed, but no RDD has been materialized. Okay. So, no materialization has been done. Okay. Now, one RDD will be materialized, okay, and hence these RDD blocks will be created on these worker nodes. So, this is block 1, block 2, block 3. Okay. So, all these RDD blocks will be created. Okay. Now, next time, and then the results will be brought back to the driver, which is the total count in this case. Okay. Now, because we had called this cache function here, okay, so it will not only create these blocks, but it will also create this cache for this cached messages. Okay. So, for this cached messages RDD, it will create this cache on each of these worker machines. Okay. Now, suppose you want to execute this same command, but this time you want to search for the string bar instead of the string foo. Okay. So, earlier for the same set of filtered messages, you are searching for foo, now you are searching for bar. Okay. Now, what will happen is, again the tasks will go to different servers, but this time instead of hitting the blocks or the actual lines here, it will actually hit the cache. So, all this portion of code will now not be executed. Instead, it will directly hit the cached messages RDD and it will filter those with bar, and then it will compute the count and come back with the result. Okay. So, this is the advantage of the caching mechanism. So, it saves for all these read operations and write operations. So, in case of interactive or iterative computation, this cache command helps reduce the cost of execution or time of execution by this mechanism. Okay. So, for example, a full text search on Wikipedia will take less than 1 second if you do cache, and if you do it without caching it will take 20 seconds, and similarly for other things. Okay. So, with this we stop our programming example. So, we have given many programming examples and scenarios where you can write machine learning programs using Spark, very complex machine learning programs, and you can also speed them up somewhat. Okay. Now, we actually go into how these programs are executed. So, we recall that we had said that whenever a Spark program is written and executed, until an action is called, only the lineage graph is created. So, this is an example of a lineage graph. Okay. But in addition, so A, B, C, D, E, F are the RDDs in this lineage graph. So, in the lineage graph all the nodes are RDDs and the arrows are showing the dependencies. But we have now gone deep into how the dependencies look like in terms of partitions. So, not only do the RDDs, so each of the RDDs will have a certain number of partitions. So, each RDD is actually present in multiple machines. So, let us say this RDD A is present in 3 machines and so on and so forth. Okay. So, now these partitions can either, so for example, the RDD B which is created by a transformation from RDD A can either have this kind of all to all dependency, that is all partitions of B depend on all partitions of A, or it can have this kind of a one to one dependency. Okay. So, there are basically 2 types of transformation. So, edges in this graph are of course marked by transformations, as you can see. So, one set of transformations like map, filter, etc., union, etc., these type of transformations produce this one to one dependencies, or also called lean dependencies. And other transformations like group by key, reduce by key, join, etc., they produce many to one transformations or many to one dependencies, depending on again what happens. Okay. So, now the way the Spark scheduler works is that it pipelines the one to one dependencies. So, all the one to one dependencies are executed together in one machine. So, even though there are 2 transformations here, this whole thing is compressed into one stage. Okay. Whereas, the many to one dependencies or the fat dependencies create the stage boundaries. So, basically this whole graph will be executed in 3 stages: stage 1 where this RDD will be computed, stage 2 where this RDD will be computed, and then stage 3 where this RDD will be computed, where the input is basically the RDD from the stage 1 and the RDD from the stage 2. Okay. So, this is how the Spark scheduler schedules the jobs or schedules the tasks. So, each computation here will be done using one task. Okay. So, we will skip this user log mining. Okay. So, now we will look at the task of another task of user log mining, and we will see an important concept called the partitioning concept. Okay. So, the task here is that you are given two types of data. One is the user data, which stores the user ID and the user info. So, think about it that users are visiting links in a particular on the internet, and you are collecting that data. Okay. So, now what you want to report is which users are visiting off topic links. So, for each user you have a certain number of topics in which the user is interested, and similarly for each link you have a certain number of topics which this link pertains to. So, you want to find out which user is visiting an off topic, or the number of users who are visiting an off topic link. Okay. So, what you do is you get the events RDD, where the fields are user ID and the link info, and then you have the joined RDD, which basically joins on the user ID. So, you know which user has visited which link in one table, and now what you want is you want to filter user info dot topics dot content. So, the topics in user info is giving the topics that the user is interested in, and similarly the topic in link info is giving the topics the link pertains to, and if this is true, then you just want to filter out those topics, or rather you do not want to use those topics. So, basically you just want to filter out the cases where actually this should be not contained. So, you want to see where user topics are not contained in link topics. Okay. So, and then you want to call count to see off topic visits, see the number of off topic visits for each user. Okay. Now, if you see your RDD will look something like this. So, here on one hand you have the user data, on the other side you have the events data, and you are having these communications for creating this joined RDD, which is there. Now, you see that this is unfortunately a lot of communication. Okay. Instead, what you can do is you can use what is called a partitioner. Basically, what you need is this kind of a graph. So, you know that your key for the joined RDD, so for all these three RDD, your key is user ID. Okay. So, what you can do is you can have the joined RDD such that the keys of these partitions are co-located with the keys of this partition. So, this will have exactly the number of partition as the user data. Okay. So, the data for the same user will be stored in the same machines as the user data RDD was stored. Okay. So, then only the events data for these particular users. So, let us say you are storing from user 1 to user 10 in this particular. So, then for all these event partitions, only user 1 to user 10 data needs to be transferred to this. So, this saves a lot of bandwidth. Okay. So, this is done using the construct called partitioner. Okay. So, what you can do is while reading the user data, you can provide this partition by cause and then you can persist it. Okay. So, when you do this partition by thing, it basically creates a partitioned RDD. So, when you join a partitioned RDD with another RDD, then the data flow happens from the events RDD to the partitioned RDD. Okay. So, this produces a more efficient communication. Okay. So, there are many operations or rather transformations which benefit from partitioning, such as join, co-group, etc., and many of these operations affect partitioning. So, basically these operations create partitioned RDDs if the input RDD is already partitioned. And then you can see that your page rank algorithm can also be speeded up using this partitioning, because what you can do is you can create the links RDD as a partitioned RDD, and in that case every time you join the links RDDs with the ranks RDD, only the ranks get copied to the links, okay, instead of every time moving both links and ranks to a third machine. Okay. So, another important topic and is what is called accumulators. So, up till now what we have seen that the machines can be thought of as the master machine. So, the machines that are used in Spark can be thought of as the master machine and the task or client machines. Okay. So, this is where all the tasks are running. Okay. Now, we know that so all the communication happen. So, all the communication for Spark happen between the task machines. Okay. So, for communicating a master variable to the task machines, we use what are called closures. So, if you define a local variable on the master and use it in a function in the mapper or the task, then this variable can be accessed in the task. But how can you use some variable which is defined in the task machine onto the function machine? So, this cannot always be done, but it can be done in certain restricted ways. So, in order to do this, you have to use the accumulator variable. So, what is the accumulator variable? So, for example, in this case you can define for a given Spark context an accumulator variable. Now, say you are you have this RDD which takes this file RDD and calls a flat map, and basically it counts the number of blank lines. Okay. And then you can say so if there is a blank, so it is so you have this file for which you are processing the lines, and if you have a line which is blank, you just increment this blank line. Okay. So, note that this line RDD is distributed onto the task machines, okay. But when the increment happens, this blank line is actually an accumulator variable which is defined on the master machine. So, the blank lines gets incremented. So, at the end of it, you can use the blank lines dot value to get the total number of blank lines from all these machines. Okay. So, finally, we get into how the execution plan is made. So, user code defines, so we have already seen that user code defines a DAG for the RDDs, okay. So operations on the RDDs create new RDDs that refer back to their parents, thereby creating the graph. So actions force translation of the DAG into an execution plan. So basically, whenever you call an action on an RDD, its so the RDD itself and its parents must be computed, okay. The job has to be divided into stages, as we have already explained, and each stage has to be computed, and basically the RDD can have one or more the computation of RDD may involve one or more than one stages, and tasks are basically scheduled and executed on the cluster. So stages are processed in a certain order, and individual tasks for computing these stages are computed, are launched on each of the machines until the whole job or the action is complete. So, each task internally performs the following steps. So, it fetches the input from either the data storage, if the RDD is an input RDD, like using either a text file or a parallelize command, or an existing RDD, okay. And then it performs the operations necessary to compute the a particular partition of that RDD. Typically, tasks are used for computing partitions of an RDD. So, for instance, executing a filter or map operations on the input data, or performing a group operation using a shuffle if necessary, okay. And then write the output of a shuffle to an external storage. So, external storage can either be memory or a local file system, as we have seen in case of MapReduce, and then this RDD is materialized, and we go forward from there to computing other RDDs as defined in the execution plan, which has already been designed. So, this is how the Spark internals work. Okay. So, in conclusion, we have seen in this lecture, which has 3 parts, the Spark, the Scala programming language, the Spark programming platform, and we have seen how to implement some machine learning algorithms using Spark, and then we have also seen how the Spark scheduler internally operates, and how we can and how basically we can speed up the various Spark programs using constructs such as partitioning and also constructs such as cache, and also how we can use accumulators and closures. So, the references for this are Learning Spark, which is the book by Holden Karau, Andy Koinski, Patrick Wendell, and Matei Zaharia. So, Matei Zaharia is also the inventor of Spark, or any other book on Spark. There are many books on Spark available, and also on Scala. Thank you.